So, from one robust design Jedi to the next, I'd like to, it's a great pleasure to introduce a colleague of mine, Martin Ebro, also a previous consultant, well, current consultant at Valcon Design for the last 10, 12 years, doing a PhD now, taking some of his insights from industry and building a theoretical basis around them. So, Martin, the first keynote speaker, over to you.
Well, thank you for that introduction. I'll present myself in a little more detail in just a few seconds. But before I do that, I assume that since it's a conference or a symposium on robust design, that everyone here would agree that robust design is important, it's valuable, it's creating value to society and to the companies that we work together with. And a lot of us are sitting developing methods to be used in industry, but I have two questions that I would like to a bit provocatively ask the audience here. When we are developing these methods, are we also thinking about how should these methods actually be implemented in a design environment? Who's going to use them and how are they going to use it in an everyday design situation? And the second question is, what's the cost benefit of actually doing it? Are we using a lot of effort to improve a few %? So is there some way where we can measure the effect of what we're doing and compare it to the cost of actually changing the way we work? And leading on from that question, I'd like to talk a little bit about why is it that robust design is necessary for production companies. And experience shows that robust design is not used that often in industry. I have some thoughts about why it's not used. Then, together with a colleague, we found 4 companies that actually use robust design as an integrated part of their development process. And we went to visit them and asked them, how have you done it? How did you implement it? How do you use it in your everyday life? And we tried to find some common traits about how robust design can be used. And we also asked them about what are the effects of using it. Do you see any positive effects on your performance? Just to understand my point of view, I've spent approximately 7 years actually doing product development, sitting at a CAD station, designing medical devices and wind turbines and whatever. And gradually I've moved on to more of a process development type of work in Valcon, where I work as a consultant and also now as a PhD candidate. So basically I've been all the way from sitting in an everyday design scenario to now analyzing how companies do design work. And hopefully that's given me an insight into both the academic and industrial world. Now, as Nils pointed out, if you ask Novo or any other company, what's your current failure rate or what's your current customer complaint rate? They all say, we're doing good. It's measured in parts per million. Very few companies actually experience problems in the market. Most likely because they've developed a very, very competent quality department and production department, ensuring that whatever comes out on the market is okay, it's of high quality. So even though every now and then we read in the news about Toyota calling back cars because of a faulty gas pedal or Vestas changing the gearboxes in their wind turbines, it's not that often that we have these visible costs of non-quality. So yeah, we do have some customer complaints, we do have some in-market service of our products, and we do have some product recalls every now and then. And that's what we hear about in the news, so we think, oh, that's where the struggle is right now. But when we talk to the companies, that's not their main problem. The main problem is that's why I have the iceberg here, is below the sea. They are actually struggling, as Nils also mentioned, with high scrap rates, rework of inventory, a lot of quality control, launch delays, milestone delays, increased R&D costs. They have developed products that are very difficult to produce, so they have tight tolerances. and variation in performance. So one batch works fine, next batch doesn't work. What happened, we don't know. So these are the things that the companies tell us that they struggle with in their everyday life. And to give an example of this, we did a small project with a company where we tried to track their use of R&D resources in different phases of product development. So here, in this graph here, you have the different phases in a typical milestone model from A to finished. And this is the percentage of the index 100. I'll get back to that, what it is. But basically, the projects sort of went fine. And here we said the usage of R&D resources at design verification, we'll call that index 100. So when we reach design verification, we've used a certain amount of money. The question is, from this point until here, how much more money would we expect to use in R&D? Now keep in mind, we're gradually handing over the project to production guys, taking over the project. So R&D should basically be phased out. So we would expect, hopefully, to have this graph sort of stay inside the green zone here as the R&D engineers pull out of the project, maybe fix a few things, and then leave it to the production guys. Whereas if we enter the red zone here, that would be a sign of, well, we thought we were done, but we were not. So this is what actually happened in these 4 projects that we measured. So out of these 4 projects, only one of them actually managed to stay inside this green zone, whereas the 3 others, sort of one even went off the graph here, used a lot more money in R&D after they thought, now we have a verified design, we are almost done here. And when I show this graph to other companies, they sit there and nod and say, yeah, we also experienced that. So I think it's not just this company. I think it's a rather common situation. And of course, if you could say, well, one thing is we use more money in R&D, that's one thing. But there are a lot of sort of effects that come due to this. The chance, the likelihood of launching on time, if you have this type of graph here, is quite low. Because all of a sudden we have to put in a lot of resources and in a short amount of time, and there's a big likelihood that we are going to be delayed with the launch of this product. And as Niels said, that could be catastrophic for Novo Nordisk. A lot of companies, now this is a consumer electronics company, they have a lot of their sales around Christmas. So if they get delayed and we're hoping to launch on November 1st and instead launch on February 1st, they lose the Christmas sales for that particular year, which could be 40% of their annual turnover on that product. So delays are quite a problem. Another problem is that you can imagine this project here probably didn't attract all the new engineers straight from university. It probably attracted all the highly skilled engineers. So they experienced a wrong use of resources because all the experienced guys are trying to solve this project, and we don't get the proper foundation for the new projects coming through the pipeline. And you could argue, well, is it us that's the problem? Is it the mechanical development that's the problem? Isn't it just the software or the hardware guys that mess it up? But actually, we looked at, again, in the same company, we looked at the change notes. So once we reach design verification, every time we make a change to the product, we have to make a note. I think most companies have this sort of system. So we sort of dove into the change notes, analyzed 800 change notes from 8 different products, and said, well, is it software, is it mechanical, what is it? Turned out that 65% were related to mechanical design. So yeah, it's us that causes these problems. And out of those 65%, we categorized them in different classes. Was it because things broke? Was it because there was a usability issue or whatever? No. It turns out that 63% were related to what we called tolerance issues or design clarity issues, so things not fitting together, things not working properly. So yes, it is mechanical design. Yes, it's the geometry that's causing these this late use of R&D resources. So this is sort of why is it important? Well, because companies are struggling with the ramp up. This is when they experience the true variation of the production system, when they go from a small series, batch series of maybe 100 products to maybe several million, as in the case of Novo Nordisk. So if it's so important and so valuable, everyone should use it, right? The problem is that there seems to be a gap between industry and academia. Surveys have shown this. There's a survey in Swedish industry by Klemmer from 2003, Araujo in 96 of UK industry, and also Thornton in 2000 in the US. And I have an example here from the first survey, asking companies in Sweden, well, do you know robust design? And out of 87 respondents, 70% said, we don't know it at all, we don't know what it is. And out of the people who knew what it was, less than 40% actually use robust design. Now this is, keep in mind, this is an 11-year-old survey. I think that in Sweden, I think robust design has come a long way, and I think more and more companies are actually using it in Sweden. But as a consultant, I've also had the pleasure of working with quite a few Danish companies, and until recently, I had never heard the word robust design mentioned in any Danish company at all. They were doing some of the robust design methods. For instance, testing. They did tolerance analysis, and FMEA were especially in the type of companies where it was required. For instance, the medical device industry, where it's a requirement that you do FMEAs. But apart from that, the term robust design was, I'd never heard it before in Danish industry until recently. So I think it's safe to say that it's not widely used in industry, at least not in Denmark. Some of the reasons mentioned in the surveys for not using robust design is that it's too much focused on statistics. The everyday engineer doesn't have the competences or time, or is not given the resources to actually do this type of analysis. There's a lack of models that give a quantitative answer. It's too complex. And it requires experienced staff. So you have to have specialists actually doing robust design. It's not something that the everyday design engineer would be able to do. And my own interpretation is that sometimes that we as engineers have a too deterministic mindset. We think that if we have a test that shows that things are okay, we think that that test is representative of the whole product, including in the variation that it's going to experience. And during the last 10, 15 years with 3D printing and the price of prototypes in general dropping, it's become so much easier for us to make a prototype and test it and sort of check it off. Yeah, this is a robust product. And we forget that this product is actually going to be produced in maybe several million copies or samples. And so a test only answers some of our questions, but not all of the questions. I had a company I visited recently which defined it this way. They had a graph here. So here they had the failure types on here. And here they had the number of times with the frequency a given failure would occur. And so basically they said, for a typical product, you'd have this type of curve. And these failures over here, so failure type 1 and 2 and 3 and so on, they occur so often that they can be discovered in a test situation. Because if all products break and you test it, it's quite easy to find it in a test. Or if 80% of the products break, it's quite easy to find it in a test. The problem was this long tail down here, so error type 47 and 48 and so on, that occurred maybe 1 out of 10 times, 1 out of 100 times. How can we actually discover these types of failures? We can't do that by testing. So we need to sort of somehow make a sort of look at the reasons for not using robust design and see if we can come up with something that's applicable to the normal everyday design engineer. And together with Lars Krosti from NTNU in Norway, we found 4 companies that actually had success in implementing robust design. We visited them, did an interview with them, asked them what have they done, and which effects have you experienced. And the 4 case companies was from 4 different countries, UK, Sweden, Norway, and Denmark. And it's a medical device company, it's an automotive company, a defense company, and an aerospace company. This is sort of the answers in a schematic form. It's just been published recently in the TQM and BE journal. I have some copies with me if some of you don't have access. And I'm not going to walk you through this whole table here, but rather talk about some of the sort of the common traits that we found between the companies. The common traits were especially in the training and the roles and responsibilities of robust design. We found that all the companies had given substantial training to their staff, to their engineers, not just the design engineers, but also to management and chief engineers, and typically in the range of 5+ days. So it's not just a 2-hour course on robust design and then you're good to go. It's a massive investment in training, considering that it's a whole department of maybe 100 or 300 people that you have to give more than 5 days of training. And after the training, they were not done. All companies had a system with ongoing coaching and support, a competence center or internal consultants that the projects could call and ask for help if they needed it. And finally, all the companies had, along with the introduction of robust design, developed specific roles related to the subject. They called it either chief and lead engineer, they called it green belts, black belts, system engineers. So certain people were given certain responsibilities in terms of being ambassadors or being the ones most competent in the field of robust design. So that's sort of common for all the companies. All the companies also integrated robust design somehow into their development manual. So it's not just sort of a satellite tool that some people could use. It was described in their development manual how to use it and when to use it. But it came in different flavors. We had the medical device company, and you can't guess which when I say they had 6 KPIs, but they had a rather strict process with these KPIs, which were presented at gate meetings. So you had to, it was given beforehand, you have to present your project using these 6 KPIs in this cockpit format. The defense company was more of a, should I say, loose kind of implementation, where it was basically simple cross-functional design reviews using Design for Six Sigma tools. The aerospace company, they required that every project used robust design tools, but the projects were given the choice which tools to use. There was a toolbox with more than 40 different robust design tools, which had been trained, and they had an internal website listing all the tools and so on. So the project could choose, well, I'm going to choose this and this tool because it's mostly applicable to my project here. But they were required to somehow use robust design in their projects. The last company here, the automotive company, they were required to define a strategy to deal with variation. So basically, they were required to think about variation from the beginning, not have this deterministic mindset where we say, if we build one prototype that works, we're good. They also had a toolbox with more than 15 different design tools to choose from. So different flavors of actually implementing it, but all of them were successful. And maybe it's also matching these ways of doing it with the company culture and so on. We also asked them, well, why do you think that robust design has become a success in your company? And they mentioned also different things. The medical device company mentioned the introduction of competent chief and lead engineers and the ongoing support and coaching. Gradual implementation was mentioned here. Again, training of the chief engineers. They actually experienced that it wasn't until in the aerospace company, they first trained all the design engineers. Nothing really happened. Then they trained the chief engineers, and all of a sudden, when they saw the light, then they demanded that all the projects use robust design, and then they got it up and running. And in the automotive company, they had a tough start because they were trying to push the tools too hard, but they managed to sort of shift focus and make it more of an internally driven process. Now, that was sort of how it can be used. We also asked the companies about, well, which effects have you experienced from using robust design? And as Niels was saying, one effect was that it has an increased transparency for management. Before, management was sort of somewhat left in the blind in terms of how the project went in technical terms. Now they had a possibility with this simple cockpit with KPIs to look at how the project was going and ask specific questions about technical details. For the design engineers, the companies mentioned that they had gotten a better insight into their own designs, understanding how and why they work, and also, which was especially useful for defining root causes when something went wrong. Stronger focus on knowledge and facts, less gut feeling and experience, as Janus also mentioned. They got a guidance on how to, what is a good design? How can we develop a good design? They got some guidance on that. Better collaboration. And another effect was actually fewer specs on the drawings. I mentioned before that one solution to having a non-robust design is having these tight tolerances and a lot of specifications in the drawings. One of the companies mentioned that now they actually have fewer specifications on the drawings because they have a design that's more tolerant of variation and is more precise which functional surfaces we actually have to measure and specify. And for the company as a whole, some of these companies mentioned they had fewer milestone delays and a shorter product development time. But these were all sort of effects given to us qualitatively. None of the companies could say, we've had a 10% reduction on this and this. So they didn't have the actual metrics to support their statements. We've tried here at ETU and in Valcon also to say, well, if we list all the expected effects that we have from robust design, which of these can we actually use to define whether we're doing good in terms of implementing robust design? There are a lot of different suggestions here, but if you also want to have them comparable between different types of product categories, so if you have one project which is a whole television, and the next project is a small headset, how do we compare data for those two? We want data that's easy to gather. We don't want to spend a lot of time actually calculating the effect of robust design. And if you want to compare the current projects with historical data, we somehow have to choose data where we have the historical data, not spending time digging up data that's not already there. So with these criteria, we actually came back to the two metrics I showed you in the beginning, which is if you can measure that the projects can do better and better in terms of the R&D resource expenditure after the design verification, then we can see an effect of that. That's quite easy to gather data on that. It's just ask the personnel department. They have all the data in terms of timesheets and so on. And the second effect could be, or second metric, could be how many change notes do we have related to design clarity and tolerances. Now, we've tried this in a company, and this is the graph I showed you before. And the first project that we tried to using some simple robust design methods, not the whole array of methods, but just one or two simple methods. And I know it's just one project, so we cannot conclude that much from it. But it actually turned out that this project stayed inside the green zone here. So it's suggesting that maybe we're doing something right here. So on that note, I would like to propose to all of you here at iSort that somehow keep in mind when we talk about exchange of experience and so on, and also because we have quite a unique mix of industry and academia here today, that whenever we talk about a method, try to keep in mind how can this actually be implemented. Does my method somehow apply to the reasons mentioned for not using robust design? Is it too complex? Who's going to use it? Does it require a lot of training and so on? And also, what's the cost benefit of this method that I'm proposing? I hope that you all have a nice symposium, and I'd be happy to answer any questions and comments that you may have. Thank you.
So we have time for some questions, if anybody has any. Okay, yeah. Go ahead.
The project you showed that where you tried to use robust design and it went well. What elements from robust design did you use? Was it mostly kinematics or materials or?
It was the kinematics and also the what we call design clarity or locating schemes or SIG stuff, trying to basically analyze all the interfaces of the products. Look at the geometry, not knowing anything about the functionality of the product, but just saying, well, these two parts, do they have a clear and unambiguous interface with each other? And by doing that, we were able to remove a lot of surfaces or a lot of geometry that wasn't necessary. Back to what Janus was mentioning, we made the parts more lean, and by doing that, yeah, that was basically the two things we did: kinematics and design clarity.
What type of company was it? Within what area?
Consumer electronics.
Oh, it was the same as the other?
Yeah, it was. Martin?
You had this study where you showed these change nodes, and you distinguished between robust design and tolerance problems.
Yeah.
That can be a difficult to tell these two apart, since you can say a non-robust design.
It's a little bit. It's a little bit misleading because they're actually these two are actually the same thing. The yellow part is where we had to change something in the 3D model because we had a clash of components or something went wrong. Whereas here we were it was possible to solve it by only changing the 2D drawing, because somehow we overperformed. Again, as Janus said, the production guys, they save us time and time again. So somehow we overperformed in other dimensions, and then we could just change the tolerance in the drawing. But it could have been a problem. So these three are somehow related. These required a 3D change to the model. This only required a change to the drawing. Yeah.
Maria Holmberg from DTI. I was wondering, most of the companies that we've seen also in the first presentation and so on are large companies, right? So what are your comments on how you can use this actually in the small and middle-sized companies? Because those are the ones that normally are at the Danish industry. So
yeah. I think it's a relevant challenge, and as consultants, we sometimes come out with the whole cockpit system and say use this, and then but we're only two guys in R&D, and so I think it's a very relevant question, and to find somehow a robust design light which can be used in companies not having the resources that Novo Nordisk has to put into this. Yeah.
Just to also comment on that, because actually removing the waste on geometry is actually not that difficult when you know the method. Making it transparent for the management, making the processes and all that is difficult, and that is demanding a big company to actually achieve that. But locally you can actually train and educate the single designer to actually remove the waste from this single interfaces. It's about very decoupled operation, meaning that it can be educated to him, and you don't need to control it, because if he's removing the waste, it will help. So that's our philosophy of actually helping the small company. Instead of putting it up to a process, let it be to the single design.
Okay. And I think with that, we'll take one more question. And
yeah, hello, Kim Smith from Delta. Just to bring in some experience from the electronics area, I work with both electronics and mechanical products. I recognize this curve you put up there, where you have, when you go to normal design verification testing, then you will only see the most important of these errors on the curve you draw on the blackboard there. But there are also in electronics new test methods, so you go exactly for the errors at the low end area, and you have to do testing long before you go into design verification. So you can actually do some kind of testing to try to find these. And then just to say, in the electronics, you tend to define robustness. You find 2 million definitions or something like that. To say it's robustness, it's large markings against both internal and external disturbances. And of course, all these internal things, that is kind of tolerant things and different issues like this. But also, there's a very big focus on external disturbance also. Yeah.
Good point. Okay, so with that, can we take that as a comment, Martin?
Yep.
Okay. So with that, I'd like to thank you again, Martin. A very interesting presentation.
Thanks.
So luckily we have quite a robust program, and we've been able to absorb up the overrun in our coffee break. It's a 25-minute break now out in the foyer, and we're back in here for past. Just in case you want to know what I'm handing out to the people, speaking of measurements, this is a wind reader device produced by one of our graduates who did a project on robust design for his final year project. And he's also been kind enough or open enough to put up the design files on the wall there. So he's a competent, robust designer. But if you've got any recommendations for how to improve the wind reader, you're welcome to go up and make some comments on the board over there. So enjoy coffee, and we'll see you back in 25 minutes. Thank you.